Good morning, everyone. Today's topic is something that nearly powers every piece of smart technology that you interact with, but almost nobody talks about it in the classroom. It's called edge computing. And by the way, the time we're done here, you're going to see internet completely differently. So let's get into it. We've all heard about cloud computing. Well, at least most of us have. The cloud is where your data lives. Google's, Photos, WhatsApp, Spotify, and all of it sits on massive servers in data centers that could be hundreds or even thousands of kilometers away from you. Now here's a problem. Imagine a self-driving car moving at 80 kilometers per hour. Its sensors detect a child stepping into the road. Well, now the car has to brake. It has to decide right now. But if it sends that data to a cloud server in another city and waits for a response, what happens? Well, obviously, the car crashes because the average round trip latency, the time data takes to go and come back, is about 150 milliseconds. But a self driving car needs a decision under 10 milliseconds. The cloud is 15 times slower over here. Now, wait, think bigger. Like by 2025, there was an estimated 75 billion IoT devices, smartwatches, factory machines, traffic lights, medical monitors, and many others that are there, all generating data constantly. Sending all of that to a distant cloud is impossible. The whole network would collapse. Well, now what do we do over here? Well, the answer to this is edge computing, and the definition is very simple. So, what is edge computing? Edge computing is processing data that is near the source and not in a distant cloud. Like instead of sending data across long distances to centralized data centers edge, edge computing processes information as close as possible to within where it's generated on the device or on the local server or on any nearby infrastructure. Think of it like this. The cloud is a large hospital in another city. It is powerful, it is centralized, and it is ideal for complex operations. But well, edge computing is the first aid kit that is right next to you. It's fast, it's immediate, and it's always available when seconds matter. Both of the systems work together and not against each other. And the three core pillars of edge computing. The first one is location. The edge servers are physically close to the users and devices. They are located in cell towers, in ISP hubs, in local data centers, or on premise servers. They reduce the dependency on distant cloud infrastructure and they enable real time processing in environments like factories, hospitals, or smart cities. The next important feature is speed. Speed. Here, low latency is very important. Data travels at a shorter distance, means it has faster response times. The latency can drop up to lesser than 10 milliseconds. This is very critical for autonomous vehicles where you need instant decision making, and online gaming where real time responsiveness is very important, or AR or VR where you need a smooth immersive experience. It reduces the lag, buffering, and delays. It supports high performances applications where each millisecond matters. And the last and the most important thing is privacy and security. Sensitive data stays local instead of being sent across networks. It reduces the exposure to data breaches, interception during transmissions, and helps with the regulatory compliance. Example, the data residency laws. It's this edge computing is very ideal for healthcare data, for financial transactions, and for smart home devices. And well, there are additional key benefits to this, such as reduced bandwidth usage, where less data is sent to cloud, so there's a lower network congestion. This saves the cost on data transfer and cloud storage. Real-time decision making. It can also be used in real-time decision making. The devices can act instantly without waiting for cloud responses. This is essential for mission-critical systems like industrial automation or emergency response systems. And edge computing is very reliable as this works within limited or unstable internet connectivity too. The systems can continue operating locally if the cloud connection fails. Scalability distributes or processing across many edge nodes. It avoids overloading on a central system. The common use cases of this are autonomous vehicles in instant obstacle detection and reaction, in smart manufacturing, in the industries where you need a real-time monitoring of the missions, in smart cities where you need traffic control, surveillance, and energy optimization, in healthcare where it is used in wearable devices with the patients and it can be used as remote patient monitoring, in gaming and streaming for reduced lag, and IoT devices, and etc. So now let's look at the differences between cloud computing and edge computing. Well, let's put them side to side so that the difference here is crystal clear. Well, in terms of data processing, the cloud centralizes everything on a faraway server, but edge computing distributes it. It's processed right next to the device that had generated it. And wait, when we come to talking about latency, the cloud gives 150 milliseconds or more. Edge gives under 10 milliseconds. So when you're talking about emergency situations such as surgery robots or like a braking system, these milliseconds are worth life and death. Now, when it comes to bandwidth, with cloud, every byte of raw data travels across the network. With edge, only the process result or the critical data gets forwarded. This massively reduces the bandwidth usage, helps preventing loss. The best use cases here are cloud wins at long-term storage, like big data analytics such as AI models, trainings, and anything like that. Whereas edge is used in real-time decisions, where like anything that is needed in an everyday basis, edge is more preferred. A simple example is when it comes to like storing your holiday photos and like vacation photos and stuff like that, you use cloud. But whether it comes to an emergency situation like a car deciding when to brake or a robot deciding what move to do next, you use edge computing. And here's what I want you to remember. They are not rivals. In every modern system, edge handles the urgent local stuff and cloud handles the heavy long-term stuff. So they're a team that work hand in hand to make the network seem work smoothly. So where exactly do we use edge computing right now? We use edge computing in almost everywhere these days. Because why edge computing is really important. Any system that really needs real-time decisions or low latency or like a local processing is already using edge-time computing. Self-driving cars, companies like Tesla, Waymo rely heavily on edge computing. The vehicle processes the camera feeds, the radar data, the GPS, and the environmental inputs. All the processing happens on board or at nearby edge nodes. The reaction times for this is lesser than 1 millisecond. This is very critical for collision avoidance, lane detection, and pedestrian recognition. Sending this data to cloud would be too slow, and even a slight delay could be dangerous. In case of smart hospitals and healthcare, the ICU monitors process patients' vitals locally in real time. The data includes a variety of data such as heart rate, oxygen saturation, and blood pressure, and etc. The immediate alerts are triggered without cloud dependency over here. It is used in remote patient monitoring and wearable health devices, thus improving patient safety and response time in emergencies. It also keeps sensitive medical data private and compliant with the regulations. It can also be used in cloud gaming, such as platforms like Xbox or GeForce now use edge servers near users. Edge servers handle game rendering, physics calculations, and graphic processing. The video is now streamed to your device in real time. Now let's look at the benefits here, such as low latency gameplay, no need for expensive hardwares, and you can play on phones, tablets, low-end PCs, on anything. Without edge computing, there'd be noticeable lag and poor user experiences. Edge computing is also used in smart factories, where edge-powered computer vision systems monitor production lines. Cameras and AI detect the defects, the misalignments, and the safety issues. The actions here happen instantly. They reject the faulty products, they stop the missions if needed, and they log data locally. The benefits of this are high quality control, reduced waste, and increased efficiency. Decision making happens in milliseconds and there is no cloud delay over here. It can also be used in AR and VR, augmented and virtual reality. It requires constant high-speed rendering of 3D environments. Edge servers handle heavy computation nearby, and headsets to receive streamed visuals in real time. The benefits here are low latency, such as there's no motion sickness, reduced device weight, it's less onboard hardware, and better battery life. It's used mainly in gaming, training simulations, and virtual meetings. And well, now to the most important case of smart cities. Edge computing powers real-time urban infrastructure. Examples, the traffic lights adapt to live traffic conditions. Surveillance systems analyze video feeds locally. Smart grids optimize energy usage. And the benefits here are reduced congestion, faster emergency response, and improved energy efficiency. The decisions are made locally and hence no delays. Additional real-world uses could be retail, where in smart stores you track inventory in real time and there's automated checkout systems and etc. It can also be used in telecommunications as 5G, where it enables ultra low latency applications, it supports IoT devices at a massive scale. It can also be used in drones and robotics, where drones process navigation and obstacle data locally, and etc. Edge computing is not just a concept, it's a real world application. Well, let's look at how edge computing is used in the networks concept. In the concept such as packet switching, in traditional cloud computing, the data packets travel 15 to 20 network hops to reach distant data centers. Each hop introduces delay, risk of packet loss, and possible congestion. In edge computing, the packets are routed to the nearby edge nodes, which is basically only 2 to 3 hops. So the benefits of this are lower latency, which is faster responses, reduced packet loss, and lesser transmission overhead. A real-world impact of this is faster video streaming, instant app responses, and reliable IoT communication. Edge computing is also used in NAT and IP addressing. Most edge devices operate using private IP addresses. Smart home devices, sensors, and autonomous systems. NAT enables communication between private local networks and public internet. At the edge, gateways or routers perform NAT locally. Multiple devices share a single public IP. Why does this matter so much? Because it enhances security, meaning the internal IPs are hidden, it supports massive IoT scaling, and it enables local communication without always reaching the cloud. An example of this is where your smart home devices talk locally via private IPs, where NAT handles external requests. Cloud computing relies heavily on efficient IP management and NAT at local nodes. It can also be used in routing protocols. The routing determines the best path for data packets. In edge computing, routers prioritize path to the nearest edge node, not a distance cloud. Uses routing algorithms such as link state routing, example OSPF, and distance vector protocols such as RIP or the shortest path algorithm, that is the Dijkstra's algorithm. The key improvements that can be made are location aware routing, and faster path convergence. A real world example of this is content delivery networks. CDNs route your request to the closest server geographically. It can also be used in QoS and congestion control. Well, not all data is equally important over here. So the edge node apply quality of service policies, which prioritize critical traffic, manage the bandwidth allocation, and control packet queues. Example of prioritization are remote surgery videos, which is of the higher priority, online gaming, which also has a medium to high priority, and file downloads, which is of the lower priority. The congestion control techniques such as traffic shaping, packet scheduling, and buffer management. This prevents network overload and maintains a consistent performance, hence ensuring that the process works smoothly. Edge computing is powerful, but it's not perfect. In fact, many of its biggest advantages also create complex engineering challenges that are still being actively solved today. The very first challenge is in hardware management. What is cloud computing? It's few centralized massive data centers. It's easy to monitor, maintain, upgrade in one place. However, in edge computing, there are thousands of millions of distributed nodes. It's located across cities, cell towers, and remote industrial sites. Challenges faced by this are remote monitoring and diagnostics, software updates, hardware failures in hard to reach locations, and the need for local maintenance teams. Example, updating a cloud server takes minutes, but updating thousands of edge nodes is a complex problem. Managing edge infrastructure is a logistical and operational challenge at a scale. Every edge is a potential attack surface. More nodes is more entry points for attackers. The risks include device tampering, malware injection, distributed denial of service attacks. Why is this harder than cloud? Because there's no single perimeter to defend. The devices may have limited security resources. The required solutions for this are end-to-end encryption, zero trust architecture, and secure boot and hardware level security. The real concern here is compromising one weak edge device can expose an entire network. Security in edge computing is decentralized and significantly more complex. Another problem is data consistency and synchronization. Data is processed across multiple distributed edge nodes. The problem is keeping all the nodes synchronized and consistent. The challenges here are different nodes may have slightly outdated data, conflicting updates, and etc. The key issue here, which version of the data is correct? The concepts involved are eventual consistency versus strong consistency. distributed databases, conflict resolution strategies, and etc. Example, two edge servers updating the same user data at the same time. Maintaining consistency in distributed systems is one of the hardest problems in computing. Cost of deployment. Well, building edge infrastructure is expensive and resource intensive. The costs include hardware, power supply, cooling systems, networking infrastructures, and skilled engineers. Unlike cloud, infrastructure must be deployed everywhere and not in just a few locations. More additional challenges to this could be scalability. While managing thousands of nodes requires automation tool and container orchestration. Keeping everything updated and coordinated is complex. Another issue could be power and connectivity constraints. Some edge locations have limited power supply or like intermittent internet connectivity. The systems must be designed to operate independently and recover gracefully after outages. And now let's talk about the future of edge computing. Because if edge computing is powerful on its own, then combine it with 5G and see how everything changes. 5G is not just fast phone internet, it's a rethinking of wireless and networking entirely. Speed up to 10 gigabytes is 100 times faster than 4G. The latency under 1 millisecond, support for 1 million connected devices per square kilometer, every sensor, every car, and every machine is simultaneously connected. And what's the smart part of this? The engineers are co-locating edge computing nodes directly at 5G base stations. The infrastructure is already being built. You just add compute power to the antenna towers. Look at this timeline and remember that this is a world your generation will build. In 2025, the edge AI chips were embedded in smartphones. Your phone processes AI to a task locally and there's no cloud needed. And in 2026, the autonomous vehicles use national edge networks to coordinate with each other in real time. In 2026, which is coming up, we use remote robotic surgery via 5G edge nodes. A surgeon in Chennai operating in a village 500 kilometers away with zero perceptible delay. In 2028, the fully immersive AR glasses rendered entirely by nearby edge nodes. In 2030 and beyond, entire smart cities are running on edge infrastructure. The network concepts you're studying here, these are the exact foundations of everything on the slide. You are being trained to build this world. Thank you.